Great. Thank you so much for the introduction. Thank you for having me. I'm really excited to be here and to chat about how we might use wearables and machine learning to improve how we interact with machines and nature. And as with many projects of this type, it all starts with the data. So it's been really exciting to see wearable sensors and these deployable sensors become more accessible and ubiquitous lately. And they're starting to show us how we can get these continuous streams of data about our activities, our health, and even animal behavior. But I think there are still a lot of questions about what exactly we can do with all of this data. So it's also natural to consider the recent advances in machine learning. And these are starting to show us, partly fueled by increasing compute power, how we can start getting some measures of understanding from these very large data sets. And so it's exciting to think about what we can do when we combine these. And by having these continuous streams of data and continuous streams of insights, we can start changing how we interact with these systems. So on an individual level, we could have on-demand physical and cognitive support. So we could teach people new skills or have more personalized data-driven healthcare. And on the larger scales, we could learn more about even system dynamics and like network interactions. But there are some challenges when we think about these types of integrations. And on the sensing side, we're going to need the sensors to be even more unobtrusive and small and robust, but also have some embedded autonomy and computation to have some of this done at the edge. And on the learning side, we're going to need to deal with these data sets that are large, but also sparse in some ways. So we're getting these continuous streams of data sets from many different people, but they can be very subject and environment specific, and they might have events of interest that are very infrequent. So we're going to need to deal with this sort of dichotomy there. But as we start to address these challenges, then we can move towards more natural interactions with machines and nature. And I often like to look to like sci-fi to get inspiration for how these types of interactions might look. So on the robot side, we can have more natural assistance. So robots that are working directly with us physically and cognitively, and that we can communicate with very intuitively. And then we can have more autonomous agents that maybe learn from these interactions and that can adapt to new situations in a way that is similar to how people might approach these new situations. And supporting a lot of these can be like smart clothing. So these wearables with embedded sensing and learning that can provide the data that fuels these and also give us physical and cognitive support. So basically like super suits that are giving us these new powers fueled by machine learning. And today I'll talk about some of the projects I've been working on towards these goals. So these include more natural assistance using wearables and biosignals, and how we can use those to build up data sets to learn about human behavior and create more autonomous human-like agents.
Sorry, I'm late.
No problem.
Thank you very much. I got confused.
And we can also move towards more smart clothing that helps provide these data sets. And just as we can try to understand and mimic human behavior, we can also look at understanding and mimicking nature. So I'll also talk about a few projects in this regard where we can use wearable and deployable sensors to study marine environments. So we have underwater robots as well as networks of robots to try to understand sperm whales. So we can start off by taking a look at making these more responsive robot assistants. And at the core here, we want to have more intuitive communication channels between the person and the robot. So we want the robot to be able to infer what the person is trying to do and then how it might be able to help. And there's a lot of different.
Could use the robots today.
Sorry?
In these buildings, it's like a maze.
Yeah. Yeah.
And I needed I got a human person in this space.
Exactly. Yeah. So I'm more intuitive to ask a person to have a
But
guy.
I could have used the robot, yeah.
Our building at MIT is the same way. I think it encourages collaboration because you need to ask for directions. But so we could think about using speech in natural language, just asking someone or asking the robot what it should do, or having like vision, force, and haptics, data flows, and biosignals. And all of these are very valuable in different types of task settings. And I think ultimately combining them will lead to very rich interactions. But for today, I'm going to focus on the biosignals and things like gloves. So these are wearable, so they don't really have occlusions or workspace bounds, and they can get very rich information about both like physical and cognitive states, which can be very helpful for working with the robot. But these signals can vary a lot between subjects. So we're also going to need some models that can adapt to changing signals over time and also hopefully adapt to new types of situations. And so to address this type of dynamic response, we can consider like a spectrum of approaches from like deep learning on one side to like heuristics and expert guidance on the other. And these all have trade-offs regarding how much data is actually needed to try to extract these understandings and how quickly you can adapt to new, like expanding the vocabulary or new situations. So we're going to look a bit at a middle ground where we leverage the human collaborator in the loop. So the person can directly control the robot when needed, but hopefully the robot can also learn from those interactions. And as we do that, we're going to build out data sets that allow us to apply these learning techniques. And we can think about how we want to scale those data sets as well. So we can crowdsource and have very large data sets of usually unstructured tasks, or we could have much more detailed recordings of very structured tasks. And one dimension we're going to be focused on in particular is looking at what happens when we scale along the number of sensors. So if we have these highly multimodal data sets with relatively structured tasks, how we can start extracting models of those behaviors. So we can take a look at how all this starts fitting together by considering how we might supervise a robot. And in this case, it's a factory robot. So we have a mock factory setup where this robot needs to choose between 3 drilling locations. And to avoid like costly or dangerous mistakes, we want a human supervisor to be able to quickly and intuitively communicate with this robot. So we did this by building out a vocabulary that captures a lot of our nonverbal commands. So like gestures and snap judgments that we might use when communicating with other people too. And we're detecting these using wearables for muscle signals, brain signals, and motion signals. And these don't have occlusions or workspace bounds, and it lets us detect both like physical states like stiffness or how much force you're trying to exert, and also even like cognitive judgments about what's going on. And one type of judgment in particular that we were looking at is called an error-related potential. And this is a signal that the brain can produce unconsciously when we notice something going wrong. So it's basically a signal in the brain that means like, stop, don't do that, something's going wrong. And clearly this could be very useful for a robot to understand. So we looked at making a classifier to detect that signal in their EEG signals. And in this case, as the classifier is continuously looking at their brain signals, and when it detects that error, in this case, the robot went towards the wrong target, the robot can immediately stop and ask for help. And then the person can use physical motions using their muscle signals to provide gestures or demonstrations to show how the robot should behave. And then the robot can update based on those interactions and resume autonomous operation. But one of the challenges that we need to address to do this is that the signals can vary a lot between people, but we want it to be plug and play for new people because we don't want someone to sit down and say, make 100 gestures, and then you can start working with the robot. We want it to be very quick for a new user to get up and running. So we looked at making, is everything okay with the stream? Okay, great. So we looked at making like lightweight neural networks and as well as unsupervised learning to try to detect these gestures and these signals. And we could take a closer look at how some of that works, starting with the classification of brain signals. So this is an example of the EEG signals from the brain. So looking down at the scalp and how a slowed down version of how the signal would look. And we know from the neuroscience literature that it occurs sort of in the central region of the brain, and that averaged over many people over time, it has a characteristic shape where it's sort of a negative followed by a positive peak. Then so we can apply some like spatial and temporal signal processing to sort of highlight that, and then pass it to a lightweight neural network, in this case, just a couple layers. But we only train the network on previous users of the system. So the new person coming in doesn't need to provide additional training data. And we apply a similar technique to the muscle signals where we are looking at forearm muscle activity to see like which direction you're moving your hand in for different gestures. And we can do some basic signal processing and then pass it to a neural network trained on previous people. But for both of these pipelines, one of the questions is that you will need to detect these on a rolling basis. So you don't know when the gesture or the signal might happen. So the neural network needs to be continuously processing these. So we want it to be robust to like shifts in the signal. And one way we look at doing this with a limited data set is through strategic data augmentation. And here's an example. Watch here so people on Zoom can see too. At the top of a gesture, moving your hand to the left. So the red trace is of the inner forearm, and that spikes up to move your hand to the left, whereas the outer forearm muscle stays relatively relaxed. And for our training data set, we center these in the classification window so that it's easier to learn on. But then we augment it by shifting them left and right. So we shift that example a little bit to the left and right and call that still a good example of the gesture. But then we also shift it far left and right and call those bad examples. So this is basically encouraging the network to prefer gestures that are centered in its window within a specified tolerance. So it has some robustness to its shifting, but it avoids more false positives. And then putting these two pipelines together, we can correct errors using the brain, detect errors using the brain signals, and then correct them using more refined motion signals. And it was interesting that in this case, it's also very interactive with the robot. So in addition to seeing that initial error signal in the brain, if the robot doesn't respond properly to that, if we have a misclassification, then the person also has another error signal that says the robot didn't do what I expected. And that can actually be even a stronger signal since they're more engaged. So it opens the door to these more like interactive frameworks as well that we can use with the brain or muscle signals.
I have a question.
Yeah.
How much training data do you need for the EEG, for the error potential processing? Because you're basically doing transfer, right? Like you're learning.
Speak slow, please.
Yeah. You're like,
I can hear you.
you're trying to detect the error potential from a completely new user. The error potential has a very specific pattern, obviously, like that, so you can detect. So what is a training procedure and for the humans that you trained on, and how many do you need?
Yeah, so we had a relatively small sample, so it was maybe only like 7 to 10 users, and each one, I believe, was about 50 to 100 trials. And then based on that, we would train the network. And we tried the plug and play version as well as small fine tuning for each user. So doing like maybe 50 trials for each new user. And that data set, the fine tuning did help a lot more. So on the order of like 50 examples for the user.
So for the training itself, do you have to have a very structured kind of like control setup, right? Or where you tell the human, or how do you detect the error potential themselves, like during the training?
Yeah, so we would light up on this, which is the correct target that the person would want the robot to move towards.
Okay.
And then the robot randomly chooses one to actually move towards, but biased so that it would choose the correct one 70% of the time.
Okay.
Because these signals really happen when the mistake is unexpected. So we want it to be mostly correct, but then occasionally have an unexpected error. And so the person needs to be relatively engaged, so like paying attention to the task, relatively calm. And then we would basically record the moment that the robot moves using a switch under the robot arm. And then we could look at that window of data just following that moment as the example. And we know, because we said which one is correct, we know if it's an error or not. So we could label them that way.
So use a robot to segment the time series.
Exactly. Exactly. Yeah.
Okay, good.
It's like a dumb question, but
No.
if the person knows the robot is going to make a mistake, and would the signal be the same? I mean,
It kind of depends how invested they are in it. So the signal really happens when it's a bit unexpected. And when your brain is like unconsciously saying, no, that's wrong, right? So to have the true error related potential, they shouldn't know ahead of time if the robot's going to be wrong or not. So that's why it's still randomized whether the robot's just going to be correct, but it's just a non-uniform distribution of whether it chooses the correct target.
So after a few trial, they kind of, lose their trust in the robot, and would that affect the system too?
It could, and yeah, that's a great point. Yeah, so because they're updating their what they expect the robot to be able to do also. So, we try to tell them, consider each one is independent and stuff like that, but obviously you can't avoid all biases. So yeah, we hopefully just have enough sample to randomize those trials out. Yeah. Cool. So yeah, so in this case, we use left and right gestures to control the robot. But we could think for additional tasks, additional robots, we might want a larger vocabulary. So thinking about how to expand the number of this communication channel. We don't necessarily want to add new training data and new networks for every gesture that we want to add. So we also took a look at using unsupervised learning to detect some of these gestures. And so some that we looked at adding were like squeezing your fist or tensing your whole arm or rotating your arm in different directions. So focusing on like this navigational control of the robot, telling it where to move. And to do this, we instead of using training data, we use more expert knowledge of what signal shapes we expect. So we can create, basically cast the classification problem as a dynamic thresholding problem, and then use dynamic Gaussian mixture models. So in each case, we would define like an indicator signal that says when the gesture is likely to be there, and that's based on the expert knowledge. And then we use real-time mixture models to have clusters, basically of a state with the gesture, a state without the gesture, maybe something in between. And to limit the data that we need, we store rolling histories of each of those predicted data. And then we periodically refit the model to the data that we see. So we could take a look at how this works, for example, using arm stiffening as a simple example. And in this case, we're trying to decide when you just tense your whole arm. So maybe you're like cringing in response to something that's going on, or you're trying to convey a stiffness response. And so the indicator signal that we define here is just multiplying the two antagonistic muscles, the biceps and the triceps. So that will be high when both muscles are activated. And that'll be the signal that we see in the left here. And then on the right is the rolling histories of classifications. But we can focus on the left where it'll label them red when it thinks it sees the stiffening gesture. And at first, the model hasn't seen any examples of the gesture, so it thinks all these little arm motions might be the stiffening gesture. But then as soon as it sees one that's a real gesture, it adapts those clusters, basically adapts the threshold, and then it can filter out all those small motions. So it's sort of doing like calibration online while you're interacting with the robot so that it can adjust to different muscle levels over time or between people. And then using that type of technique to detect all these different gestures, in addition to the neural network for the original one, we can control more fine-grained robots like teleoperating a drone. So in this case, we have a suite of gestures for navigation, and we can detect the gestures at any time. And across, I think this was about 6 users, over 2 hours of using the drone, it detected about 82% of the gestures. And in an offline case where they weren't actually controlling the robot, maybe they focused a little bit more on their gestures, it detected upwards of like 95% of the gestures. So this was promising for being able to expand the vocabulary without needing a lot of training data, but obviously it needs some expert knowledge to cast that problem as a dynamic thresholding problem. And we also started extending this towards more continuous motions, although in this case, it was all more discretized. So that took a look at how we might use like muscle signals, brain signals, these wearable devices to create these more natural communication channels using nonverbal commands. But we also want, in addition to directly controlling the robot, we'd like to start learning from these interactions. So how can we build up, a data set from these, or how can we, in general, make the robot more autonomous in a way that might be human-like? And a project that we've looked at doing that is called Action Sense, where we're building up this highly extensible framework and multimodal data set of human behavior. And we want to be able to record these demonstrations using wearables so that people can do the task the way they normally would, so recording natural human behavior. And then we're hoping that this can move towards like foundational models of physical intelligence. So models that have a sense of how people perform physical tasks and how they might move and how they might reason about them. And then ideally generalize to different types of applications. So we'd like to train robot assistants that move more naturally or that perform tasks in a human-like way. And also look at helping transfer skills between people. So models that can learn from experts and help teach novices using like haptic feedback or other ways of giving real-time feedback. We could also have more immersive virtual worlds and also inform how we design smart clothing. So thinking about which sensors are most informative for different tasks and how we would go about making those sensors. So in the current data set and reporting framework, we record the muscle signals that we saw before, but then augment that with full body tracking from IMUs, as well as finger tracking. We have custom tactile sensors on the hands for touch. And we also have eye tracking to get a sense of attention. And all of these modalities can provide different information, and we're looking at how they can be analyzed together. And we also synchronize these with global sensors, so like cameras and audio, to get more of a sense of ground truth about what's going on and what the person is trying to do. And we also have activity labels, so annotations throughout the data. And the software is extensible to different sensors. It's a modular framework, so hopefully moving towards like a repurposable, reusable framework for human studies and recording from these types of sensors. And it also allows the experimenter to annotate the data in real time. So they can make notes as the experiment is going on and reduce post-processing work.
I have a question. As you know, Nadia, I am much smaller level, but she thinks about these things. So I am curious, you have this picture here. It calls for an interesting architecture. Have you thought how you are going to organize the architecture?
The architecture for the learning
Because
model or for
You are
the,
going to collect a lot of data. You have to make a lot of decisions because the muscles is not one muscle. It's a bundle of muscles.
Mhm.
And you have to somehow organize how you are going to control that bundle. So it's not just one muscle. So it's a parallel, but also multi-processing system, I see, especially since you are considering many different sensors.
Mhm.
So what's your answer?
So one option, right, is to train models that get a sense of each sensor, like to have a modular learning framework. So to have a model that learns about muscle signals and how that influences your motion, a model that learns about attention from video. And then put those models into like an ensemble framework where they can use them all together. Another option, right, is to just have one large network, put everything in and hope that it can learn all of that. And I think these different types of approaches might be based on how much data you actually have, right? How much data you can collect to support those.
You have to get more details in order to convince me.
Oh, sure. Yeah, happy to chat about that more in depth.
I will not push it.
One thing that I was thinking about when Rosanna asked this question was, I mean, all of these sensor streams, they are acting like at different time scales, right? Like, first of all, they have different frequencies at which you're streaming the data, right? Like, EEG, you can get up to like 1 kilohertz, like that. Depends, like all of these have different frequencies at which you can get the information. But it's not just that, it's also the fact that some of these data streams have features that happen at different time scales as well, right? So from my point of view, plugging it into a big neural network, that's not gonna work. And that's not gonna work, and it's not gonna work at you just by thinking of like, if we have more data, it's gonna work, probably not, because all of these streams have different meaning, and it's not just about, you know, putting all of these data streams together and like stacking them all up and hoping that something learns. Like the intention of moving comes from the brain and then passes through the motion and then through the muscles and then goes to the actual like motion of the arm, for example, or one of your limbs. So there's like, the signal is traversing in time, right? So like, I mean, I think since you gather all this data set, these data, you might be able to analyze how these things are moving and how each of these different sensors are being activated, or like what component is activating at which time.
Mhm.
If and then you can come up with an architecture that takes into account all of these, like also these connections in terms of time, right? Between the different sensors.
Yeah, definitely. And depending on the part of the task you're looking at too, right? So like object manipulation or how to actually perform a motion, that's going to be much shorter time scale than say like the higher level reasoning of I need to move this plate into the dishwasher.
Yeah.
Right. So you can impose different structures of when to use different sensors based on the horizon that you're looking over.
Well, for the sake of the students, I would say this is more than one PhD thesis. Because it's a very neat thing about, okay, to flexibly adding new information, new context, so. So as I said, it's more than one PhD.
Yes. Exactly. We're just starting to scratch the surface of it now. It is, so I tend to agree that, we need this a priori knowledge of how these sensors might relate, how these time horizons interact, and then we could put that into how it should process it. The other school of thought with the large model, just to come back to that, is if it were to work, right? Like a lot of what we put in a priori might be, switching between sensors at the times or filtering signals so that it comes down from the high bandwidth, things like that, right? And these are types of transformations that could theoretically be achieved by weights in a network. Right, so if you gave it enough data, it might be able to pick out those types of transformations on its own. But I agree that we're not quite at that scale yet. And I think whenever we have a priori knowledge, it's best to include it because it will always help them out. So far, we've been looking at kitchen tasks with this framework. So we've recorded about 20 tasks that span like things like food prep, cleaning,
Is involved.
manipulations, and like tableware tasks. And one of the reasons we're focusing on kitchen tasks is because it's a common target for robot assistants, where we want someone to help us out in the kitchen. But also they're relatively structured and well-defined tasks that still have like many different strategies to approach them. So it's an interesting use case for studying these types of behaviors. And they also, like we were mentioning before, some of them isolate more lower level manipulations and are very short, while others have longer horizons and are like, setting the table or loading the dishwasher. So looking at some get more at the reasoning side, some get more at the object manipulation side. Then for each of these, we have this composite multimodal synchronized streaming. So here's an example where in the center, we have the body tracking from IMUs. And then at the top, we have a first person video with the green dot showing where they're looking. So attention through the eye tracking. And then we have the left and right arms, where in the top are the touch sensors. Depending on signals, you can kind of make out a hand oriented this way that lights up as they're interacting with the objects. And then we have muscle sensors and motion sensors. And so it'll be interesting to see like how we can combine these in different tasks and which ones become most important over different scales. One that we're starting to look at how we might train a model to learn from these demonstrations. And right now, we want to see if we could have more human-like motion control. So more fluid robot motion than like a typical robotic motion. And part of it is getting at what it means to be human-like motion. And part of it is just seeing what we can learn from these demonstrations. So we're starting out looking at short tasks like pouring water. So this is a pretty structured, well-defined task, but it still has generalizable trajectory traits like smoothness. And then we can process the wearable data to extract, like simulations to look at in a simulation environment, and also to create features that could be passed to a model. And then we can also try these out on the real robot, in this case, Baxter, to see how they operate, in the real world. Then right now, so we're developing this pipeline to go from wearable demonstrations to robot control. And now we're thinking about what types of models we could put in the middle so it could be adaptable to new situations, like basic things like move the glass or the pitcher to more high-level reasoning. And we started with some just like recurrent neural networks with some custom activation functions that look promising for generating these types of trajectories. But we're probing it a bit more now about how we can generalize to new tasks. And then we're hoping to also use these to explore metrics of what it means to be human-like motion. So we're wondering if these models can embed some notion of maybe like smoothness or effort that it takes for the person to move, or ergonomics, things like that. So yeah.
I know water and electronics don't go well together, and I noticed you didn't have water in your picture, and I'm curious, is that a direction you're interested in? Do you have thoughts on what added complexities there are when you start using medias that start moving away from a strictly rigid body?
Yeah, so it also gets at dynamics of moving bodies, right? So, and part of that comes into the robot control then. So right now we were focusing on just replaying the trajectory and leaving like the details of dealing with moving water to say the robot controller, where we command this end effector, we just kind of assume that it can do it. But yeah, the scaling up the complexity, it'd be great to see like how these interaction forces of the actual object could be incorporated. Yeah.
How many demonstrations do you usually need for?
Sorry, could you say how many demonstrations?
Yes.
Yeah, that's something we're exploring now too. So right now we have, like for the pouring water, we have about 50 demonstrations across like 3 people. So still a pretty small data set. But seeing how different people are as well. And I think it depends again on what you're trying to extract. So if you're just trying to learn that the trajectory should be smooth, then you probably don't need too many demonstrations. If you're trying to learn more about the actual intention and the goal, then you could scale it up.
So what are you learning exactly, or what are you mapping from the human demonstration? Is it just the end effector motion, or is it also the joints motion?
So the model right now, so the features going in are like the joint angles of the arm, as well as, you know, mostly joint angles, but also like orientations, things like that. The model currently predicts all of those. So it would basically predict the actual human arm pose throughout the whole trajectory. When we're doing the robot control, we're just focused on the end effector. So we just do standard inverse kinematics to get the rest of the arm. But we're hoping to evaluate things like effort and ergonomics. We could use the full output.
Yeah, because the joint configuration.
Yeah, that's a.
Like, and then on the robot.
Yeah. Focus on this part.
Yes,
Ignore the arm behind the curtain. Yeah.
I mean, I wonder why, because, I mean, you have the information of the glove of the tactile sensor, right? So you can actually learn also like have a feedback, like learn a feedback policy of pouring the actual water instead of just trying to imitate the trajectories.
That's right. Yeah, yeah. Exactly. And you know, part of what we're putting in here too is like the effort of like how much you need to activate your muscles and stuff. And we'd be interested to see if we can predict tactile information like from muscle activation. So seeing like what subset of the sensors are actually carrying that information. And then as we start looking at these models, we're also excited about scaling to different types of applications. So, you know, like additional kitchen tasks, but also things like sports. And some of our collaborators at GIST in Korea actually used our action sense framework to record data sets of badminton and like strength training. So we're interested to see if we start applying these types of models to all these different domains, what might come out as being similar. So this took a look at moving towards these data sets of continuous behavior to move towards more like human-like autonomous agents. But to scale this up, right, we're going to want even more unobtrusive sensors, more sensing that's embedded within our clothes itself. So that has sensing and computation kind of woven together. And one project that we started looking at that is making a soft glove with embedded machine learning. So this uses soft sensing to detect pose, and then it has embedded model running on board to detect sign language. And the way this works is we have a commercially available conductive knit. So this is a glove that has silver threads woven throughout it, and it's meant for like using your touchscreen. But as the material stretches along the knit pattern, the electrical resistance between points on the glove changes. So as the fingers bend or as they touch each other, you're going to get changing resistance values. So we can take advantage of this to create strain sensors by tying wires to the glove at different points as readout points, and then measuring the resistance between each of those points and a common ground. And this ends up creating soft strain sensors that span the degrees of freedom of the hand. And we also add an accelerometer to detect overall hand motion. Then the microcontroller that's running on board collects all this sensor data, does some signal processing, and then actually runs a LSTM neural network that was pre-trained to classify these signals. And similar to what we saw with the muscle signals, we also do some data augmentation and like dynamic calibration to help it be more generalizable. Then to test this out, we trained it on 24 gestures from sign language. So we did 12 letters and 12 words that include both static poses and dynamic gestures. And it was able to distinguish between these quite well, which was very promising, although we're still exploring how it generalizes across time, because one issue with soft sensors is that they can change as the material stretches, as different people use them. So we're still exploring through time, but in this case, we did like leave one experiment out cross validation, so we could try to predict how it would do on a newest session of using the glove. And we did some ablation studies that confirmed that it was using both the pose sensing from the soft strain sensors and the accelerometer motion sensing. And then the pre-trained network, we deployed on the microcontroller itself, and it was able to detect the sign language in real time by classifying the streaming data. So this helps move more towards like an edge computing paradigm where the wearable is self-contained and has both the sensing and computation on board. So we can hopefully use these to like analyze and assist communication or more behavior more generally.
I'm curious, at one time in my lifetime, I did many things. One of them was studying how many fingers do you really need. So did you look at that?
We haven't looked at that, but yeah, that's
Because
interesting.
It turns out that the last two fingers are not critical and they add to your complexity. So you want to simplify. Do you see what I'm saying? So on the other hand, the palm is very important. Support.
Remember, we had started looking at that a few years ago, and my brother-in-law is like a composer and pianist, and he was very intrigued. So we ended up taping some of his fingers together and say, "What can you still play on the piano? Like, can you?"
For a piano player, then you need to.
Yeah.
So depends on what you want to do.
Sure. That's interesting. Were you looking at particular tasks or in general, like how they use over time? Okay. This is a quick overview of how we might move towards more embedded clothing, like smart clothing with embedded computation and sensing. Now, a lot of these same tools that we use for making natural assistants, autonomous agents, and wearable sensors, we can also use to not only understand human behavior, but to start understanding animal behavior and nature. And so we can take a look at how we can use the wearables and deployables in this context. And one of them that we created a while back was a soft robot fish. So this was looking at how we can use this deployable device with embedded computation to unobtrusively study coral reefs and unobtrusively monitor fish. So the idea is that it would be biomimetic, so it's a soft tail that moves in a way that's sort of similar to how a real fish would move, so that it hopefully doesn't disturb them while we're trying to monitor them. And it has embedded computation on board for basic operations, like performing low-level motion control, and then we're also starting to look at adding in like machine learning from computer vision. And so right now it has the camera on board, but we were looking at adding other sensors too to monitor like water quality, how the animals are behaving, things like that. And right now we interact with a diver through an acoustic communication device. So we can have sort of a shared autonomy approach where the diver is giving it high level commands to carry out, and then the robot fish can perform them more autonomously. So we're starting to see how we can use these types of deployable devices to monitor large marine underwater ecosystems. And then we're looking at how we can scale this up. So one natural direction is have more of these robot fish, and we can have swarms communicating together. Or we could start looking at having networks of different types of sensors and different types of robots underwater. And so this has been a large collaboration called Project SETI, which stands for the Cetacean Translation Initiative. And we can have small underwater robots like the fish, but then we also have passive listening stations that we're trying to set up. We can have like underwater gliders, drones in the air, and even tags or sensors on the animals themselves. And so this is looking at how we can create these large multimodal data sets of animal behavior. And then we're working directly with biologists, linguists, all sorts of different disciplines to set up machine learning pipelines that can extract insights of interest in these different cases. And we're starting to look at this to study sperm whale language. And so I wanted to share a few